All right, everyone. I am here with Jamie Macbeth. Jamie is an assistant professor in the Department of Computer Science at Smith College. Jamie, welcome to the TWIML AI podcast.
Thank you. Thanks for having me.
Hey, I'm super excited to dig into our conversation and learn a bit about your research and what you're up to. Let's get started by having you share a bit about your background with our audience. How did you come to work in AI and cognitive systems in particular?
Sure. So originally I would say, a physicist, actually, a mathematician and a physicist, as an undergraduate and also sometime as a grad student. I then fell in love with computer science. I studied computer science in graduate school. And towards the end of my career in graduate school, I also fell in love with the specific topic that I work on now, which is artificial intelligence systems and cognitive systems for performing natural language understanding and the issues associated with that.
That's great. That's great. When we were chatting earlier, you spoke a little bit more about your the way you think about cognitive systems and kind of how that's different from a lot of the contemporary application of machine learning and AI. I'd love to hear you elaborate on that a bit for our audience.
Sure. Yeah. So those of us in the cognitive systems community, we're a part of the artificial intelligence community, but people in the cognitive systems community are focused quite a bit more on using artificial intelligence as a vehicle for a better understanding of human intelligence, and not particularly of using AI to just score well at particular tasks and do well on the leaderboard. I think some of the negative things that have been associated with artificial intelligence these days, such as biases and things like that, have to do with there being a little bit too much hype around the systems that people are building and the way you're able to show good numbers at these test problems, and focusing less on the actual science. Okay, what really can these systems do? So yeah, in the cognitive systems community, or I care much more about building systems that have a human-like intelligence.
Yeah, it's an interesting contrast. I think we see all the time in popular media nowadays. Researcher publishes a paper about AI scoring well against some benchmark, and then journalist writes article, AI learns to understand XYZ. And you must be like, no way, not understand.
Yeah. I agree. So I think that things that have happened in the machine learning community, I think we've machine learning, artificial intelligence have come a long way in the past couple of decades. But I think another thing that's happened is that we've begun or not begun, but there has evolved a particular kind of machine learning research that's just focused on doing well, scoring a little bit higher than the last person did on that one particular data set. And then what I found in my work is that if you scratch the surface a little bit, you find that there are important issues with things like the metrics that people are using, and the possibility that you have systems that are fairly overfit to particular data sets. You throw adversarial examples at a system and you see it kind of crumble. It's unable to really do the things that you thought it was doing because it scored well on that data set.
Mm-hmm. So when you talk about AI as a vehicle for better understanding human intelligence, what are some examples of that? Ways that we understand human intelligence now better because of AI research?
Yeah, that's a great question. my examples for this come from the kind of decades ago traditions of AI. For example, Roger Schenck and Robert Abelson's original work on scripts, goals, plans, and understanding, and that's a text, or those are ideas that have kind of permeated a large path through many different through many different communities, including the cognitive psychology community, the cognitive linguistics community, even people performing social science. Quote this idea of scripts, which basically that means that there are knowledge structures that people use for navigating commonly encountered social situations. So I think that's a really good example. That book from 1977 is still cited. It's got tens of thousands of citations, and people still cite it over and over again. And when I talk to social scientists who know about this concept of scripts, they don't even realize that it comes from artificial intelligence research, but it's an important concept that people use across many disciplines. So that's a good example, I think.
Got it. Yeah. Great to hear you mention that book. It doesn't get mentioned on the podcast very often. I think it's come up once or twice before. Okay. I went to grad school at Northwestern, and I think that's where Roger Schenck was for quite a bit of time. And that was the first book that I ever came across about AI. In fact, I picked it up at like a used, either like the used bookshelf at Barnes and Nobles or like a flea market or something like that. You also talk a little bit about, you mentioned that a big focus from an application perspective for you is on natural language understanding. How does that tie into the broader goal of your cognitive systems work?
Yeah, what you end up realizing when I started studying this, I knew what lots of people conceive as natural language processing. What I understood was, you just have these systems that are calculating statistics having to do with words or parsing to figure out what the grammatical structure is of a sentence, and maybe doing some things like that. What you eventually realize is that if you want to build systems that are performing something like the way humans understand language and produce language, because language expresses ideas, you realize that your systems need to be able to represent ideas and manipulate ideas and basically have thought representations. So your systems that at first you think natural language processing is just about messing with words and grammar, you eventually come to the conclusion that natural language understanding is about building systems machines that can really think like people, if you're really going to get it to understand that text and say, answer a question about that text.
And so are the tasks that you're focused on the same tasks that we see, traditional tasks in the NLU community, like question answering?
Yes, yeah, that's one important task, not the only thing. I mean, you can think of others such as translation or summarization and things along those lines. But more recently, folks in the machine learning, natural language processing community have started to generate large data sets that have those tasks in them, that have things like, a data set that has paragraphs and lots of questions and answers. But when you scratch the surface of the machine learning, deep learning systems that are working on those tasks, what you find out basically is that they're taking advantage of patterns in the texts and in the questions in order to come up with correct answers to the questions according to what's in the test answers for the data set. And if you change things around just a little bit, all of a sudden the system doesn't really understand. But yeah, those are things like reading a story and answering questions about the story, summarizing a story, paraphrasing a story. Those are the kinds of things that I work on.
Okay. And so in the I don't think traditional is the right word here, but in the typical NLU setup, you've got this task of, let's say, question answering, and you're just trying to perform well on the question answering data set. You're not necessarily trying to perform well, you're trying to gain deeper insights into something. What are the things that you're trying to gain deeper insights to, and like how do you approach that problem, or what's your problem set up, and where does your learning come out of thinking about these kinds of problems?
Yeah, one of the deeper insights I want to get to by looking at, say, story understanding or question answering is how do people form a mental picture of what the text describes? How do people create that mental picture, and then how do systems manipulate that mental picture in order to be able to reason about the text and also the questions that were asked about the text? And the main thing I found in my work, the most important thing to me is that it turns out, ironically, that to represent knowledge, thought, meaning well, you have to have a significant part of your representation that really has nothing to do with the language at all. It really has to do with these imagery, mental model pictures that you create that represent the meaning, and then those get mapped onto language. They get mapped from language in understanding to that representation. And then when people say things or produce language, the idea, which is this non-linguistic conceptual structure, then gets mapped back onto language. And that's one of the important things I've found in my research, and an important thing I'm trying to get to by looking at tasks like question answering or paraphrasing, because in many ways that's what paraphrasing is. You realize that to say, well, there are many different ways of saying the same thing. That same thing stuff must be this other thing that's different from the language, the ways of saying it.
Mm-hmm. Yeah, I'm wondering what that means in practice. Like, I think of models like a deep learning model is building some representation that is, some vector space. Is what you're saying that? Are you adding additional constraints to that representation that says that it has more image-like properties that should I be taking what you're saying about building a picture literally, or is that more figurative?
It's in some senses literal, in some senses figurative. When it comes to say, for example, artificial neural networks or deep learning systems that are professed to be able to build their own representations, the problem that I see is that I haven't seen people demonstrate very well, particularly when it comes to natural language processing problems, demonstrate well that the representations these systems are building are like the ones that I think we should be building to build natural language understanding systems. So deep learning you're supposed to be building your own. The system's supposed to be building its own representations. It's not obvious based on the inputs that deep learning systems are being given. Say, for example, examples of paragraphs and examples of questions and answers relevant to those paragraphs. It's not clear that the deep learning systems are building that they're building representations that are like the ones that I think probably would be good for representing things. In my opinion, the representation systems that I work on, for the time being, I'm building them by hand. And these representation systems try to decompose meaning into complex combinations of conceptual primitive structures. For example, if I said something like, Mary kicked the ball on one hand, and I said something on the other hand like, Mary moved her foot towards the ball and struck it. I didn't use the word kick in that other expression, but you're still in that other expression able to compose a picture of what happened, and see that it's equivalent to the first sentence that I gave. So I've been building systems by hand that can start with a conceptual structure that looks like this. It's got these decomposed conceptual primitives, like for example, for kick, one conceptual primitive meaning that Mary moved her foot, another primitive act meaning that the foot struck the ball, and another primitive act meaning that the ball took off and went somewhere. And then I have these other systems that actually can generate lots of paraphrases of this conceptual structure. It can generate language from it. And then what I've been doing in some ways is feeding these paraphrases into deep learning systems that supposedly can understand language, and finding that they don't really.
Mm-hmm. So when you talk about this representation that you're handcrafting and you're creating equivalences between kicking and moving feet, is that within the natural language domain, or is that in some vector space, or are you mapping to some kind of image-based representation of these things, or something totally different?
Yeah, these kinds of representations have been studied. They've been studied by AI people. Before we were talking about Roger Schenck, and we were talking about Scripts, Plans, Goals, and Understanding. If you read that book, you might have remembered the original restaurant script had all these conceptual primitive acts in it, such as the waiter P-transes his or herself themselves to the customer, and then leads the customer to the table, and then the customer M-transes their order to the server, and things like that. So those are so Schenck had this system called conceptual dependency, and the idea was that try to reduce the number of primitive acts that you have to represent things, and then to represent more complex things, just add more primitive acts to make it more specific. So that for the time being, those are the kinds of representations that I work on. They have primitives such as some object moving through space, some object moving to the inside of another object. That was called ingest. Some object moving from the inside to the outside of another object, expel, and then other primitive acts like that, trying to break things down in kind of molecular structure kind of way. There are other systems that people have developed in the cognitive linguistics community, specifically these systems called image schemas that were popularized by Lakoff and Johnson. And in research, we're only just now over the past few years figuring out some of the correspondences between Schenck's old system of conceptual dependency and these other systems that were developed by people in the cognitive linguistics community, and trying to learn from them. Sorry that if that's kind of too long, kind of a long answer.
That's awesome. That's great. I'm wondering about, you kind of, as part of the setup, you talked about how deep learning systems, as an example, are often overfitted on a given benchmark, and there's a lot of competition in the research community to one up the next in achieving state of the art performance on a given benchmark. Is your research? Are you like saying, hey, I'm not going to play that game, I'm trying to get understanding? And if you're opting out of that game, how do you evaluate the performance of your representations?
Yeah, that's a great question. So in some ways I am not playing that game, and in some ways I am playing that game. So in recent work that was published at the Advances in Cognitive Systems conference last summer, what I did was basically, and I think I described this a little bit earlier, there are deep learning systems that can do paraphrase recognition, and there are data sets that are devoted to training and evaluating systems that can read two sentences and determine to some degree whether those sentences are paraphrases or not. So what I did is I took one of those systems, and then I took a system that Schenk and his students worked on at Stanford in the early 70s, and I enhanced it. And what this system does is the system was called Margie. And what it could do was you could input some natural language. It would translate it over to this non-linguistic language-free conceptual representation, conceptual dependency. And then it could, based on its language-free thought representation of the original sentence, it could generate paraphrases of the original sentence. I enhanced the system so that it could generate a lot more paraphrases than it could in the 70s, because, in the 70s, the computers that people had and the systems that people had were very limited. And so I generated a set of tens of thousands of paraphrase pairs that meant the same thing. And I also tested that these pairs meant the same thing, because I sent them to crowd workers and asked, okay, do these sentences, you think these sentences mean the same thing? And overwhelmingly they did. Then what I did is I took these pairs of sentences that all meant the same thing, and then I sent them to one of these, well, I didn't send them, but I used one of these deep learning paraphrase detection, paraphrase recognition systems. And I asked this paraphrase recognition system, okay, do you think these sentences mean the same thing? And what was interesting about the sentences that my system generated was that they encompassed a wide range of linguistic variation. They were able to express the same idea using lots of different words and different syntactic structures. So you had sentences that meant the same thing that maybe only had one word in common, and syntactically they were very different. And humans looked at these pairs of sentences and said, yeah, those mean the same thing. The deep learning systems that were trained to do paraphrase recognition and detection, they fell off a cliff when the sentences stopped using similar words. And you got to the point where the sentences were not using the same words at all, meant the same thing. The deep learning system was basically like a coin flip. Half of the time it would say they were paraphrases, half of the time they would not. It was basically just guessing, because it wasn't really understanding what the sentences meant. So in that way, I play the game a little bit.
I was just going to push a little further on that and try to have you explain in that context, what are you benchmarking your system's results against? Like, is it, it's not necessarily trying to, maybe the goal of this research was to identify the deficiencies of the deep learning systems, and your metric was the number of paraphrases that they couldn't recognize, or the performance. But I'm curious, do you ever compare the performance of your representations against the performance of a deep learning type of system? Or are there other ways for you to understand whether the systems that you're able to create with your representations are more robust? Like, it also does. It does strike me that, in some ways, maybe the metrics aren't rich enough. Like, if I'm envisioning a scenario where you're creating these paraphrases that are so much richer than what a deep learning model might create. And, is the metric, have we created the metric for richness? And what is that? Expressiveness? Maybe the traditional competitions aren't really judging the things that your representations are better at. But I'm also wondering, broadly, like how, if you opt out, like, how do you compare, and how do you know when you're on the right track, and when your research is getting you closer to understanding?
Yeah, you raise a bunch of important questions. Let me try to address each of them in turn. So in the study that I was describing, there are metrics that you can apply, but there are metrics that, well, not metrics, but we did statistical tests to determine that basically humans were better at recognizing that the sentences in this set of paraphrase pairs, that these paraphrase pairs, humans were better at seeing that these sentences meant the same thing, and we're able to perform statistical tests showing that humans saw that they meant the same thing, whereas the deep learning systems that we were testing, they basically declined in performance with greater degree of linguistic variation. You raise the important issue of, well, if linguistic variation is important, what are the measures for doing that? And I've developed some measures for linguistic variation, such as you can do things like, if you've got a corpus of text, if you've got two different corpora of text, you can do things like parse all the content and then look at things like what were the part of speech tags that were given. What is the distribution of the part of speech tags that were given in this data set versus that data set? And I did that in a previous study where I was trying to better understand the differences between human caption generation and machine captions that were generated by the typical deep learning systems that people have used for caption generation problems. But I think it's something that needs studying these kinds of metrics is something that I want to work on in the future. There is work that there are projects that I'm working on now where I'm hoping I'll be able to actually build systems that. So I talked to you about this paraphrase generation system. I'm working on systems now that ideally can do the opposite. They can read and understand language and bring it into this non-linguistic form. And we're using a data set from a data set called ProPara from the Allen AI Institute, I believe. And this data set has these texts that are about ProPara is short for process paragraphs, and these texts are about things like geological processes and physical and chemical processes, and we're going to treat those like they're stories. And that data set has tests that you can use to see if your system is really measuring up. So that is part of our plan. But I think the larger issue of having the right metrics is important. When it comes to judging these systems that perform paraphrase recognition, the metrics that are usually used are these bag of words metrics, like, for example, the BLEU metric. Basically, what they do is they take they want to compare one text to another text to see if they're kind of the same, and they just treat each text like a bag of words. Like, it doesn't, the metric doesn't care about the order in which words come in, and things like that, where you could have rearranged the words and totally it could have meant something different. You're basically just trying to get your system to throw the right words in there that are relevant to sort of relevant to the thing. You can say the same thing with different words, and then your metric doesn't really work anymore. So, but generally, this is an issue with the kind of research that people are doing, where they just want to score better than the last person on that data set. And so they don't really care what the metric is very much, or whether the metric means anything. All they care about is their score.
Mm-hmm. In some ways, your research makes me think of folks like Josh Tenenbaum at MIT. His is, I think less natural language focused and more kind of visual. At least I think about it like that. And a lot of what he'll talk about is trying to kind of capture and understand this idea of common sense and you know, external a priori knowledge or things like that. Like, is that part of what you're looking to understand in your research in the language domain?
Yeah, yeah. I'm flattered that you mentioned Josh Tenenbaum when talking about or thinking about my work, and then you think of Josh Tenenbaum. I'm very honored that you would say that. And yeah, I think that we are interested in many of the same issues. I'm trying to remember the term that Josh Tenenbaum uses. I can't remember it at the moment, but I do believe that from what I've heard him talk about, that he is interested in trying to figure out what the most abstract conceptual primitives or structures that people are using to kind of break things down and understand them. I think he's I've seen him do some interesting and important work involving children and their interactions with people around certain kinds of tasks that involve reasoning and social interaction and things like that. Yeah, I think it's great and important work. And so that's something I'm interested in too, is if you believe like me that there are some structures that some cognitive structures that people evolve, or let's say people develop at a young age before they even learn language. If you're going to say that there are these kind of pre-linguistic representations that people are using and they're building language on top of those representations, you'd be interested to know what those are. And I think there are folks like Josh Tenenbaum who are getting or trying to get at what that is or what those things are. But perhaps not so much doing it through language. I'm you can see I'm trying to do it through these tasks that have to do largely to do with language and texts. Yeah.
Mm-hmm. Mm-hmm. In the kind of traditional deep learning approach, like the knowledge of the system is kind of stored in like weights and embeddings and things like that. It's kind of inherent in the model. It sounds like your representations are more external. Yeah, I wonder if there's anything you can elaborate on there. Does your work have this kind of traditional view of a model, and how does that relate to, when you're building systems around your representations, like what do they look like? Are they similar to what we might be used to with deep learning and machine learning, or are they very different?
They would, in many ways, they would look like, in some ways or in many ways, they would look like structures, kinds of models and kinds of systems and structures that were way more popular, perhaps in the 1970s and 1980s, when what people would call symbolic artificial intelligence, good old-fashioned artificial intelligence, mm-hmm. And some people characterize them also as rule-based systems. So I've been building a lot of systems by hand. And
are you okay with all of those? That terminology, or are you air quoting it because you don't really like those terms?
Well, right. I'm air quoting it because if you say symbolic AI, I have no problem with that. Yeah. I guess the reason why I air quote it is because people have negative associations with those kinds of technologies where you are building things by hand. So, mm-hmm. Historically people know that there have been ups and downs in artificial intelligence, AI winters, as they're often referred to. And there were AI winters that were associated with people building rule-based systems, symbolic systems where we're actually coding things by hand instead of using machine learning. And so my view is that people kind of made there's kind of a general negative association with doing any sort of building systems by hand, and I think part of it is because the old AI tradition, people thought about this idea that you'd have expert systems that were able to replace people completely. And so what people came to realize is, man, there's so much that people know and so much that I would need to encode on my own that there's no way I would ever be able to, if people were working around the clock, lots of them, just encoding this knowledge by hand, it's impossible that we'd ever be able to build a real system. Notwithstanding Doug Lenat and Cyc and projects like that. So, but my point of view is different. I'm not building systems by hand in the hopes that I would eventually be able to build an artificial general intelligence like that I was coding by hand, and I would eventually be able to encode all of the knowledge that people have. But I'm using symbolic systems, building systems by hand, or you can say you can call them rule-based systems if you like to, if it's not too pejorative. I mean, the reason why I build these systems is to help try to understand what's going on, what the representation should be, so that when we turn to say, okay, we're going to now use machine learning to try to build systems to do these tasks, we have better ideas, instead of kind of what I see today is there's deep learning, right? And it seems like people think that deep learning can do anything as long as you supply enough data to it. But then the question is, what kind of data should we supply to it? If we just supply text, is there stuff that we know that helps us understand text that is outside of the text itself? And do we also need to supply that? And so that, that's why I'm not opposed to building systems by hand. And in some of these studies, what I've done is I've built systems by hand that are able to, say, for example, generate lots of paraphrases as an example, and create a data set like that demonstrates, okay, maybe these are the kinds of representations we should be aiming for in our deep learning, machine learning systems. I think the new target. So right now, the way things are is that people build these data sets, say, for example, paragraphs, questions, and answers, and the target is to just try to get the deep learning system to give the right answer. In my opinion, the new target should be that you should be supplying data sets that help deep learning, machine learning systems build the right representations. And those representations might be non-linguistic or language free. And in turn, those representations help you get the right answers. And then you can see, oh yeah, this thing is really kind of thinking the way I want it to think. Whereas right now, it feels like deep learning is just giving us a black box where we can't quite see inside and see whether the representations it's building to solve the task make any sense.
Yeah, that the way you describe that resonates really strongly with the conversation I had just the other day with Peter Abbeel. I was a researcher out of Berkeley focused on robotics, and we were kind of comparing and contrasting his views as an academic, thinking about kind of end-to-end deep learning, and as you said, just throw enough data at a problem, and his more evolved views as an entrepreneur and a roboticist that's trying to solve problems for companies, and the need to try to capture and incorporate knowledge that we have about these problems. And he made this really interesting point that if you say, okay, we want to incorporate this knowledge that we have about a problem, one way to do it is to build rules into your system, build your if-then statements or whatever that looks like. But what he's said that struck me as really interesting was another way to do that is to use your rules to generate more data for your deep learning systems. And so in that way, you're kind of training them on the cases that you know a lot about, but still not having to, not having to take on the technical debt, if you will, of having a lot of rules, the brittleness of rules, that kind of thing. And it strikes me that maybe your systems could be used in a similar way. Like, you've demonstrated the ability to create these really robust paraphrases that, could be really interesting augmented data for a paraphrasing system that you might want to train. Maybe that is the kind of glue between your world and the deep learning world.
Yeah, that is one way. I mean, so anytime you come up with an adversary, anytime someone comes up with anything that shows that hey, the deep learning system isn't really doing what you want, then the natural, what the folks who are doing big data, the machine learning will just say, I think many of them will probably say is, well, okay, just give me the data that you just created that made my system.
Give me the examples. Yeah.
Give me those examples and I'll just feed them in. And then my system will then be able to handle those kinds of, will be able to handle those adversaries and will be better as a result. That's one way of looking at it. But then from my standpoint, it's I can continue doing work on these representational issues, and perhaps generating data. But I think generally. I think generally it's one way to interface between those communities. I should say, though, also that I think part of the reasons why in the expert systems era that the rule-based systems people had a lot of difficulty was that they were using in many cases perhaps they're using certain kinds of logical inference engines. And I think the issue with logic is that what people mostly tend to do is they create logical symbols that correspond to words. They don't necessarily create symbols in those systems that correspond to non-linguistic conceptual representations that I think we have. And so I think if we're creating knowledge structures and reasoning systems that have more of that non-linguistic, language-free, abstract, primitive decomposition stuff, that we could do much better, even if we're not going to use machine learning at all. If we were just back to building expert systems like we were in the early, I suppose in earlier decades. If we were back to building those expert systems, if we were using better representations, those systems could have been better too. Maybe we would not have failed and had AI winters the way we did.
Mm-hmm. Mm-hmm. What are, kind of looking forward, what are you most excited about in terms of directions for your research?
Yeah, so the systems these representational systems that I keep talking about, for the time being, we find that things are much more straightforward when you're talking about things that are happening in the physical world, like Mary kicking the ball being decomposed into someone's, Mary's foot moving and striking the ball and then the ball moving, and things like that. One thing that even in earlier decades where they were working on this research of trying to come up with these non-linguistic representations, that they never, in my opinion, they didn't really get a good handle on. And this is also true if you read Scripps, Plans, Goals, and Understanding, was, well, how do you decompose the idea that someone should have a goal, or how do you decompose the idea that someone should have a plan? How do you decompose a decision, or other kinds of activities that involve thought? And they had I feel like they got stuck back in those days and didn't make much progress in figuring those things out. They, in many cases, created um, more and more diverse kinds of structures without doing the decomposition into primitives thing that I think made their work in the early 70s more cool versus their work in the mid 80s or so. And so that's something that I'm in future work that I'm curious about and interested in. Again, about scripts, plans, goals, and understanding. One of the important basic ideas from that book is that some of or some important reasoning evolves from your episodic memories. So remember the restaurant script, the idea that you tell this story about Mary going into the restaurant, ordering, she eats the lobster and leaves, and you're able to reason that she ordered the lobster from the server and all these other things. And those knowledge structures are built out of, or at least theoretically, the theoretical idea is that those knowledge structures are built out of your episodic memories of your experiences with restaurants. Mm-hmm. So then you start wondering, well, what if other kinds of reasoning actually work that way, where you can build lots of script structures representing people's common experiences, and that's how people do a lot of their reasoning. And a lot of their reasoning may involve scripts combining with each other to reason about unusual events, such as what happens when you have a birthday party at the restaurant. You combine the birthday party script with the restaurant script, and then you start reasoning about things like, well, if so-and-so pays for my dinner, is that considered a birthday gift at the restaurant, something like that. And so that's something I'm really excited about, is learning more about general reasoning through these structures that are meant to represent people's episodic memories, just people's experiences, rather than saying, well, it must be first order logic, or I guess on another, if you take it the other way, it must be deep learning is the only way, or something like that. So, can you start building databases of scripts or databases of episodic memories, and start using those as the basis for structures for reasoning and things like that. So those are just a couple of examples of things that I'm really excited about in the future.
Awesome. Well, as always, we will link to your website and some of your recent work on the show notes page that will be available when the episode is published. Thanks so much for taking the time to share a bit about what you're up to.
Thank you, Sam. Thank you so much, everybody, for having me.